Hello, everyone. Thank you for coming to my session, and thank you to the organisers for inviting me. So, at the end of Snoofer last year, you guys published a paper, and one of the things that stood out to me was that there was a real need for new hardware and software that performs well for spiky neural networks to sort of push this field forward, especially to larger problems, both in terms of neuron numbers and data sets. So that's kind of what these preliminary results relate to. So a lot of people in this field are currently using sort of existing machine learning tools for simulating SNNs, and these tools underneath the hood represent the spiky neural network as a computational graph. So in the most naive representation, you have your input coming at the bottom, you multiply it by a weight matrix, and then you perform some sequence of fundamental operations to emulate a lift neuron. So, for example, you add the input to the current state, decay it, and apply a threshold operation, and then you get a binary activation vector, which you multiply by the next layer of weights, etc. So, when you implement this on a GPU, each of these operations in the naive approach is an individual kernel. And this is bad because each kernel has some kind of fixed latency, so it's sort of order of microseconds on Linux, but still it sort of adds up. And also between these fundamental operations, you're writing data back to global memory, which is definitely unnecessary. So by using just-in-time compilation, which both TensorFlow and PyTorch do, or by using custom kernels, which I believe NORS, which Jens is going to talk about after me, does, you can merge these kernels together into single kernels, which obviously reduces the latency. But the latency of these models still scales with the depth of the network, which is bad, especially when you're thinking about deep networks. And it also is repeated every time step. So every time step, you're getting this latency cost. And more fundamentally, these computational graphs are executed sort of in dependency order, which in the case of a feed-forward model means sequentially. So the model has to be as wide as the GPU. So you have to have enough hidden neurons you have to have enough neurons in each layer to occupy a GPU, which generally means large batches, which is generally found in machine learning more generally is not necessarily great. It doesn't scale forever like that. And finally, spike propagation is not matrix multiplication. It's more just like summing the rows of the weight matrix where there's spikes. So theoretically, that's a much cheaper operation. If that's true on current hardware or not, it's a different question, but theoretically, it's cheaper. So as anyone that's seen any of my talks over the last 5 years is not going to be surprised to see, the work I'm presenting here is going to be involving our GeNN simulator. So GeNN is a C++ library for generating SNN simulation code. It's now got backends that can generate CUDA, OpenCL, and C++ code, and everything you can do in GeNN can now be done from Python. It's the level of abstraction is still somewhat lower than tools such as like NORS, but it's all you can do a lot of stuff from Python. And part of the reason for this lower abstraction is that previously the focus has been on computational neuroscience and neurorobotics. And if you're interested, there's papers listed at the bottom of the slide where our previous results in this area, and the link to GeNN itself here. But throughout development of GeNN, this maxim has been to maximize the user control. So as a user, you can fiddle with a lot more stuff in GeNN than you can in typical SNN simulators. And we think this means that it's well suited to sort of have a new life as a backend for high performance spike-based machine learning. And hopefully I'll convince you in this talk. So SNNs and GeNN are represented in a very different way. Spike transmission is not instantaneous, so you can break the dependency between the layers of neurons, which means that you can simulate all the neurons simultaneously and all the synapses simultaneously. And this also means the model doesn't need to be a direct acyclical graph. And within these layers, you can do various fusing stuff, so you can simulate them using a sort of minimal amount of code. And we talk more about this. We talk about how the details of this fusing in our most recent paper. And by doing this, you also reduce this latency. So the latency is not quite comparable because this is sort of pipelined. Like you have to wait a number of time steps before you get any output. But after that, like a pipeline CPU, you're going to get a much lower latency output. So what model are we going to? So in this work, we're using this very simple model. So we're training small recurrent networks. So these are basically, you've had some input neurons project to a densely connected recurrent population, and these connect to then all the recurrent neurons connect to an output population. And what a lot of people in previous talks have used backprop through time to train very similar networks to this. So we're taking a slightly different approach. We're using a sort of approximation of real-time recurrent learning, specifically this symmetric, this eProp rule, which this awesome paper by Belek, Sher et al. From last year presented. And this is only one. There's lots of learning rules that do the same approximation. And this, for me, this paper by Friedman and Emre from this year, like really sort of clarified the link between all these learning rules and backprop through time. So I thoroughly recommend that. But anyway, in these models, we have a simple lift neuron model with adaptation. So there's a second state variable with a longer time constant and a relative reset. So every time you get a spike, you subtract something from the membrane rather than setting it back to zero. There's a non-spiking output neuron, which basically just low-pass filters the output of the network. And each synapse in the model has not one, but two eligibility traces, epsilon and E. And the weight update is a simple difference, is you feed back the difference between your targets, which are these pi k t star, and the softmax of yk, so the softmax of the output. You project this back to your recurrent population. In our case, we're just using a transpose of W out, which is B, and you just sum these over time. So this is kind of a sum loss function, and this is applied to all the recurrent weights. And we don't actually, you could do this online. We don't choose to do that. We want to use optimizers and stuff. So we sum up these weights, these delta weights, until the end of the batch, and then we apply them to the weights all at once. But nonetheless, this could be an online learning rule. So we've added some extensions to GeNN. This new version 4.6 was released yesterday-ish. So you can now do batching, which is important for fully occupying a GPU when you've got small models like these. So this means, you can instantiate multiple copies of the model, and you can choose to share variables between the instances. So you can have weights that are shared across all batches in a typical machine learning sort of configuration. And the second main feature is these custom updates. So as well as neurons and synapses, you now have these custom update stages, which you can use to implement arbitrary operations. So in our case, we use this to implement stuff like atom optimizers to turn the sum of delta weights into actual weight changes. And also, this system supports sufficient matrix transpose. There's plenty of computational science papers on how to do efficient matrix transpose on a GPU. So we've just taken one of these kernels and implemented it. So we don't need to care about the weight transport problem right now. We can just use an efficient transpose at the end of each batch. And also, we've implemented reduction operations with some more syntax in these custom updates. So you can reduce across many batches the gradients to get a weight to form a single weight update. It also supports NCCL to go across multiple GPUs. So like a lot of people, we've been looking at the spiking Heidelberg digits. This is about 10,000 recordings with 12 speakers speaking the digits 0 to 9 in English and German. And these are converted to 700 spike trains using a realistic model of the ear. So we're comparing here against, against some of the results from Friedman and Tim Vogel's paper from last year, where they trained small lift neural networks using backprop through time. And in short, using a feed forward network, they achieved somewhere around 75% accuracy on this task, and around 80% if they use a recurrent network. Using one of these LSNNs trained with eProp and GeNN, our feed forwards models are slightly worse, but as are our recurrent networks, but only very slightly. Like this is probably within the error bars. And we can overcome this by just throwing a few more neurons at the problem. Because we're not using backprop through time, there's not really any problem to use more neurons. And by doing this, we can exceed the performance of the backprop through time trained network. So how fast is the training? So this is the other thing. So Here we're training this is a training time for this model. We're comparing PyTorch, the PyTorch code that comes from SpyTorch, and GeNN using this eProp LSNN, and we're training both of them on a relatively large batch size, so batch size of 512, so we can fill our big GPU. And you can see at the small scale, GeNN is a bit slower, but by around 700 time steps, GeNN starts to win out, and by 1,370 time steps, GeNN is significantly faster than PyTorch. So basically, just because we're not using backplot through time, we can train longer for faster. And if we go into a bigger model, like PyTorch is clearly faster. This is because PyTorch is taking advantage of the tensor cores on our GPU, and we aren't yet able to do that. But backplot through time runs out of memory. This is on a 12 gigabyte GPU, so it's a massive GPU. But you can't train 1 second of activity on a 512 neuron network. Whereas in GeNN you can, and similarly on 1024 neurons, GeNN is still slower because we're not taking advantage of the tensor cores, but we can train many more time steps. GeNN wouldn't run out of memory for a huge number of time steps, but there's not really much point in a bigger network here. So that was one data set. The other data set we're looking at is a spiking sequential MNIST. So basically, in this data set, you take the MNIST digits and you scan across the pixels in time like this, and each you have somewhere in this case 79 neurons, and each one represents a threshold crossing. So when you hit some threshold crossing, you get some neuron activity. So this data set was used by this pretty cool paper that came out earlier this year by Wolfgang Master's group, and they compared a whole selection of hardware, which we're going to get to in a minute. But basically, they were also training LSNNs, so adaptive neural networks with TensorFlow, and they got so they trained LSTMs and they trained these LSNNs, and both of them got kind of 95-ish%, I think maybe 96 on the LSTM. And then they trained some feed-forward. They trained some purely lift networks, which performed much worse, so around 60%. Here, GeNN doesn't perform quite so well, or sorry, the eProp doesn't perform quite so well. So we were getting sort of closer to 90, and this only increased slightly with the number of neurons. So this is clearly a task where you need to consider the gradients flowing through the recurrent connections. But nonetheless, 90% of this task is still pretty good. So in this task, we also looked at inference performance, which I think is the most interesting result here. So on the right-hand panel, we're comparing the same GPU running TensorFlow and an LSTM, which we saw as performing sort of 95%, and our recurrent LSNNs implemented using GeNN. And you can see in the top that the latency is lower with GeNN using across all batch sizes. The gap reduces as you get larger batch sizes because we don't batch quite as efficiently as TensorFlow yet. But still, this is a really good result. I think this is the first time that there's been shown there's sort of any performance advantage of using SNNs on sort of standard hardware over ANN models. So they also, in this paper, they also use this energy delay product. So basically you multiply the energy taken for your simulation by the latency. And here again, running using GeNN and SNN, you have a lower energy delay product. So these are all batch sort of with large batch size data sets, but we also looked at batch size 1, where you can start to compare some other stuff, so including low-EHE, which they used in their paper, and TensorFlow running on a CPU. So these ones of stars are numbers we've taken from the paper, and the other ones are ones we've run ourselves. So in short, TensorFlow with batch size 1 is both slower and uses more energy, and TensorFlow also because it's very simulating LSTMs is very compute heavy, performs very poorly on the CPU. Whereas GeNN, even at small batch size, is significantly faster, and in fact significantly faster than low-EHE. Also, GeNN can also generate simple CPU codes, and this was even faster than GPU here because with batch size 1 you can't really occupy your model properly, and SNNs are not particularly maths intensive, so CPU code can be remarkably good. And if we go to the energy delay product, you see a similar story. Like GeNN uses less, the energy delay product is much lower on GeNN on CPU or GPU. The only thing that beats it is low EHE, which is hardly surprising. So that's me done. Yeah, I'd like to thank all the people at Sussex who've helped with this work. My funders at the EPSRC who have agreed to continue to fund us for the next 5 years, which is very exciting. And various other people, including Gregor Lentz, who was the author of Tonic, without which this work would be much more painful. Okay, thank you very much.
Great, thank you very much, Jamie. Cool. All right, so we have some questions, and also to the audience, if you want to ask some more questions, we'll probably have time for more questions than we've already got. So actually, the first question is going to come from Tim Masquelier. So he says, how does the memory required for your approximated RTRL scale with the number of neurons?
So it scales the number of neurons in the same way as any other forward pass in a neural network. So you have the additional memory per synapse of the eligibility traces, but there's no extra memory with each time step. So memory use doesn't scale with time. That's the key thing.
Okay. Yeah. And the next one is from me, which is it's like going back to some old-fashioned things. So I was wondering, how efficient is this efficient matrix transpose, and could you use that to speed up the sort of more classical STDP thing that we all used to do before we were doing this sort of thing?
I mean, so it's basically as fast as copying the data around the GPU. So yeah, so it's basically as fast as reading the data from global memory and writing it back to a different bit of global memory. But you still wouldn't want to do every time step, which is why we're still using a sort of batch. We're using this kind of hybrid batching approach where we only do this copy after your batch is completed.
Can it also work with a sort of with a sparse representation, or does it then stop being so?
This particular algorithm doesn't. But you could also, as you say, use the kind of online matrix transpose stuff that many people have done with STDP.
Okay. Yeah. Yeah, because I guess at some point we're all going to start thinking about how to do all of this stuff more sparsely. And
indeed, yeah, this is still fairly dense in the learning phase.
Yeah, yeah. Oh, there's another question from me. Sorry. So I'm wondering if you're using this sort of approximated RTRL and not using backprop through time. Does that lead to biases in the sorts of solutions that you find?
I don't know. In short, I think, yeah, I don't think anyone has really explored that. No one's really explored that problem. That kind of space. I mean, as I understand it, the sort of theoretical difference is that that eProp doesn't take into account the gradients that flow through the recurrent connections themselves. But clearly, the recurrent connections do improve the performance. Yeah, it's not totally clear. We need to find a data set where it's more apparent, perhaps, because as that 2021 paper showed, if you sort of what's the word? If you artificially sort of constrain backprop through time to ignore those gradients, you still get roughly the same performance. So it's not totally clear.
Yeah, well, exactly. I'm not sure that you could even answer that question.
Like we have tried it in some tasks where if you kind of think about the solution yourself and try and like just assemble neurons to do it, it doesn't come up with that solution, even though that solution seems fairly obvious. But yeah, that doesn't really mean anything in the space of gradient-based algorithms, I don't think.
No, indeed. All right, so last question then is from Thomas. How about scaling for multiple GPUs and multiple hosts with multiple GPUs?
Well, I've actually got a slide to answer that, Thomas. Yes, so we did some scaling experiments across multiple GPUs using both a system with 8 V100 GPUs and another system with multiple nodes with 4 A100 GPUs. And you can see that basically within a node, so kind of from here down to here, you get pretty close to perfect scaling. It does start to drop off across nodes, but still, I this is using NCCL, which is the same library that TensorFlow and PyTorch use. So I would expect the scaling across GPUs and across nodes to be pretty similar.
Cool. All right. Well, with that, I think we'll say thank you again to Jamie, and do go and check out GeNN. It's a great piece of software, and we'll move on to our next talk. Thank you very much.